Welcome back. Today we're going to be talking about some new concepts, but before we get too deep into those, I wanted to go through some vocabulary and just introductory ideas. So first thing, specific heat capacity. You'll sometimes also see specific heat. That is the amount of thermal energy that we need if we want to raise a sample that is 1 gram by 1 degree Celsius in temperature. So if we look at the example we have here, and this is something very common that you'll be using quite often, this is the specific heat capacity for water. So if we want to raise a 1 gram sample of water by 1 degree Celsius, we need to use 4.184 joules. Remember, that's that joules that's coming back. You want to remember that idea. So our specific heat capacity, that capital C or sometimes lowercase c value, it's going to be 4.184 joules per grams degrees Celsius. And it's going to be different for every substance that you're dealing with. This one is specifically for water, and you'll have different values for metals or non-metals and just every substance you see on the periodic table, as well as every different compound. So let's talk about how those specific heats compare. If you have a high heat capacity, that substance can take on a lot of thermal energy with only a very small increase in temperature. So the example I'm using here is water, because you'll hear this example quite often. Hopefully you remember back to our solutions unit, we introduced water by saying that it has a high heat capacity. So if you have our oceans on Earth and you want to measure how the sun warms them up, notice that the sun can heat the water all day long for years and years and years on end without that water just boiling away. It can take on a lot of thermal energy without increasing too much in temperature. That's a very good thing for us. We as humans kind of like a comfortable range of temperatures to live in. If it gets too cold, it's just too cold for survival. And same thing if it gets too hot, we also can't survive at those temperatures either. So we rely on our oceans to really regulate those temperatures in our atmosphere by taking on that thermal energy that would otherwise cause something to increase drastically in temperature. So high heat capacity, water, very, very helpful for us. You can also have something with a low heat capacity. So these substances are going to be good conductors of heat. So what that means is you can add just a little bit of thermal energy, and all of a sudden these substances get very hot and can carry that heat really, really well. So for this example, think of the metals that make up the pots and pans in a kitchen. If you want to cook something, if you put it directly into a metal pot or pan, it is going to heat up very quickly and potentially burn whatever you're trying to cook. Whereas if you add some water to that pan and try to cook the same thing, it'll go much more slowly and be a much more gentle cooking, so hopefully it doesn't burn. And that's because that water can take on a lot of that heat, so it doesn't get too hot. Whereas the metals, very low increase in temperature will cause those metals to heat up. You can also think of like a metal slide on a playground, for example. During the summertime, that gets extremely hot, whereas if you want to go swimming in a swimming pool, even if it's 100 degrees outside, that water is not going to burn you. So let's look at a couple more things. If we want to measure that amount of heat that you have to add, we have a couple of things that we can talk about. So this equation that's found on your reference sheet, this Q is equal to M times C times delta T. So what does that mean? So Q is measured in joules. And the way I know that is because our mass, which we measured in grams, the specific heat capacity, which is always given in joules per grams degrees Celsius, and then our delta T, T is dealing with temperature, that is degrees Celsius. Notice that the Celsius will cancel and the grams will cancel, leaving us with joules. Something else I want to point out, if you're dealing with delta of something, that tells you that it is a change of something when we're talking in chemistry. So for delta T, that is our change in temperature. We're saying that's our final temperature minus our initial temperature. You may also have seen it written with a little f for final and a little I for initial. Either way works. Just remember it's final minus initial and not the other way around. So if we want to, for example, use water, that joules per grams degrees Celsius is going to be that 4.184 that we talked about. And then you can figure out how large is the sample you're dealing with for water, and how high are you raising the temperature, or how much are you decreasing the temperature? What is that change in temperature? And that'll tell you the amount of thermal energy needed. So this is a formula we're going to use more in the next video. I just want to introduce it to you here so you understand the introduction. Some other things we can talk about. If we say 1 calorie with a lowercase c, you'll also see it written as 1 cal. That is equal to 4.184 joules. So that's based on water, of course. So 4.184 joules is equal to 1 calorie. We have a couple of other things, and you have this conversion also written on your reference sheet. 1 kilocalorie, or kcal, is equal to 1 cal with a capital C, which is also equal to 1,000 calories lowercase c. So I know it's a little bit confusing. You probably won't see it very often to see cal with a capital C, but I just want you to keep that in mind in case you encounter it. More often than not, you'll see cal with a lowercase c and kilocalories, just to keep it from getting too confusing.